Well, thank you very much for having me, and a perfect time because it's the end of the day, and this is going to be a very simple talk, a very unsophisticated and a pedestrian way of doing things. So hopefully that goes over well at the end of the day, as I said. Let's see. Oops. Can I advance this some differently? Okay. Forward. Oh, okay. Oh, okay. All right. So just to make this clear here, so QCD2A is adjoint QCD in 2 dimensions, and actually the group is going to be SUN. So not some sophisticated group or anything like that, but kind of the usual model that has been around for literally 30 years or more. So here's a couple of the first decade or so, and then recent interest, as you can see here in the last couple of years, we actually had a lot of names here that are in the audience that are interested in this theory. So let's go right to it, because we actually had a talk this morning about DLCQ already, and so a little bit of the introduction. So let me give a little bit of motivation here. As is known, of course, since a long time, adjoint QCD is very insensitive to a number of colors. And so here's, for instance, this DLCQ work of Igor and collaborators that shows that the first corrections are 1 over n squared, and the coefficients are very, very small, right? So the question naturally arises, why is this? And some in the audience might already know the answer here. There's of course some theoretical work that has been done before, but as I said, I want to do this in a very pedestrian way. So let's jump right into the light cone Hamiltonian. So if there's some questions about the framework here, this is a very naive way in some sense, or for some of you at least, where we just use ordinary light cone quantization, and we use the light cone gauge. And so, issues that could arise with these choices, we basically map out at this point. And the Hamiltonian here has basically 4 terms, and the big realization that was already done way back when in the 90s by Pinsky and Minuccio is that the contractions that partially cancel the singularity, it does not actually have any finite n corrections. And so naturally, the question is, what takes over at finite nc when we have a new term, the so-called d term, or I could call it the d term, that only has to be taken into account at finite n, that basically has to take over and cancel these singularities. Otherwise, we would not have a finite theory, right? So basically, you can already expect what the punchline is, that in order for that theory to be finite, you have to have a cancellation of not the operators, obviously, but something has to cancel. And as it turns out, a lot of the matrix elements will cancel. So what we have to do is act with the Hamiltonian on the states of the theory, and then just classify the terms by their power of n, and basically where they come from. So states at finite n are pretty much what you expect them to be. There's multiple trace states with wave functions, which are just distributing the momenta between these traces. And the integrals here look a little bit forbidding, the boundaries of these integrals, but they're basically there to ensure that you're working on your proper Hilbert space here. And what I've done based on previous work is actually that I've simplified this a little bit and wrote this on a Hilbert space that's really the union of cyclic permutations of the unique Hilbert spaces that would actually give you fairly complicated expressions. All right, so if we do a quick sanity check here and say, okay, does this sound right? Are these the right states here? We can actually do this 2 ways. We can do a good old DLCQ multitrace or finite n calculation. We get a wave function, or we can actually use this method ELCQ, the exhaustive exhaustively symmetrized Light-Bloom quantization, which gives us, due to symmetry calculations, symmetry considerations, actually wave functions that we can just write in and multiply them together. And lo and behold, we get basically the same wave function. Wave function is 0 at some points, which might be a little bit alarming, but really this is nothing else but a matching of the harmonic resolutions k at these different of these different traces. All right, so the notation, as I said, we were going to apply the Hamiltonian to the states, and naturally what we get are tons of states, tons of terms out of this. And these terms we want to just give a good notation to. So let's do the notation where we take into consideration the power of Nc by just a number next to the operator or next to the term, and then A, B, or D are the origin of these terms. So they come from the A term, the B term, or the D term. And then since they're going to be either trace diagonal or trace joining or trace splitting, let's notate this also with this either underline or overline or tilde. One additional thing that we need is a dagger for, if we create particles, because we have also particle diagonal terms and particle non-diagonal terms where we can change the particle number by 2. A lot of the terms will actually come from not from the Hamiltonian itself, but if you commute through operators, and that's pretty much the only sophistication, if you can call that we have to do. We just have to commute through some fermion operators, and so we get 2 terms there, and one is down by 1 over n. If we do this, just the kind of not to preempt this too much, but basically a preview of the results would be that some of these terms, so the A2 term and the D2 term, again, remember these are 1 over n squared terms, they would actually the matrix elements, I should say, would cancel. The operators themselves do not cancel, but the matrix elements, if they're sandwiched between states of definite trace number, of definite Parton number, they would actually cancel. And there's a bunch of other cancellations too. So this is all kind of what we expect from the physics, from saying we have a finite theory. So we should actually have that cancellation to make sure of that. But there's other operators or other matrix elements of operators that do not exactly cancel. There's some partial cancellation, but not a perfect cancellation. So we have to conjecture pretty much that that has to cancel. The matrix elements between actual physical states have to cancel. So this would be kind of an outlook that is ongoing work still. What I've done so far is just basically done the exact cancellation state. So if you write down these terms of the Hamiltonian or the action of the Hamiltonian on these states, you get a bunch of terms that you can diagrammatically write up like this here. So you have terms that are for the leading terms, which are the 0 terms with no dependence or like leading in n all the way down to down by 1 over n cubed. This is, not to hang up too much on this. A bunch of terms, you write them down and you figure this out. Then you see what the matrix elements of these terms are actually are. So here, write down the Hamiltonian. Luckily, we already know at least some of the audience love Hamiltonians, right? We had that already. So here's the Hamiltonian, which can be broken down by trace blocks, right? Blocks of different traces. So the trace blocks and then the Parton blocks where we change Parton number or can change Parton numbers, and that all looks kind of like a mess because we have lots of terms, right? So the idea is, of course, that we show that a lot of these matrix elements will cancel, and so we end up with a much simpler Hamiltonian, right? Here's what this looks like. Again, this is not pretty maybe. But it is very straightforward, right? Literally act with the Hamiltonian on these states and figure out what the matrix element is. It's going to be a bunch of sums and a bunch of signs and a bunch of deltas because you have to match all these spectator momenta and so on. And at the end of the day, this whole sum turns out to be 0, right? So this is that's pretty amazing, really. But again, in hindsight, kind of a moment where it's say, I should have actually expected this. It's just like in usual DLSQ calculations, we never actually check the matrix elements themselves. We generate the matrix, we put them in our favorite diagonalization routine, and out comes the spectrum of the Hamiltonian, right? And so what I'm telling you here is basically that there were already a lot of zeros in there. So these cancellations, this weak sensitivity to the number of colors really comes from the cancellation of these matrix elements. So basically, before you even get to the diagonalization, you actually have already your Hamiltonian, which is very, very sparse in some sense, and that is in some blocks, right? So these D-term matrix elements, as kind of anticipated, really exactly cancel the A elements. It's a little bit surprising also because of the factor of 1/2. There's a factor of 1/2 in the D terms, but this is exactly compensated by the number of terms that you have being just twice the number of terms. So it's a little bit like miraculous or so, but I'll get back to this one here. Of course, you can check this with the DLSQ matrix, and indeed this works out. So are there any more cancellations? And as I said, yes, there are. So we have, of course, we need to cancel all the A terms, the singularities at finite n. We need to cancel them somehow with the D terms. So that all works out. But we have that one case of the 1/n contributions that do not exactly cancel. We can also look at partial number changing terms. That is maybe initially a little bit less interesting because we have, of course, no physics that guides us there, because there's no singularities, so there's nothing that should or has to cancel. But as we see, there's also a lot of canceling there. So if you look at this, a lot of these matrix elements also turn out to be zero, and that seems a little bit suspicious there, right? So that's probably some kind of a general lesson to be learned here, and maybe that lesson has already been learned. I'm actually talking yesterday to maybe these guys figured this out already a long time ago. So I have to look a little bit more into this. But here's, as I said, a very kind of pedestrian way of really seeing this happen. This yeah, this is the I think the finite volume. Oh, okay, all right. So the simplified Hamiltonian is up there. So pretty much we lose a bunch of these terms. Anything that is higher order than or more complicated than 1/n squared goes away. So no 1/n cubed, no 1/n to the fourth. They would be down anyways at large n, right? Or even moderate n. So no only 1/n and 1/n squared corrections. And then, of course, these are non-diagonal. So if you want the correction to the spectrum, then you need to take two of these, and so you get naturally the 1/n squared that the DLSQ will actually tell you is the right dependence on the number of colors. All right, so we have a simplified Hamiltonian, and of course, it's the question here is can we push this a little bit farther? So can we actually do this in the continuum limit? And if you run the DLSQ on this, then it turns out that a bunch of these matrix elements indeed show signs that they want to kind of go away in the continuum limit, where you get less and less non-zero matrix elements. And what I'm working on right now is basically to set up a calculation, a continuum calculation. So basically sandwich this. Now that I have the Hamiltonian matrix elements in the single momentum basis, just sandwich them between the DLSQ states, or between eigenstates, basically. Or at least asymptotic eigenstates, and see if indeed these matrix elements cancel. So this is ongoing work, as I said. This looks initially a little bit forbidding because it's a finite n, but it turns out we can simplify this greatly, and it looks right now to me at least just like a generalization of work that I've done before. at large N, it's just needs to be generalized in the sense that it can insert spectator momenta at will anywhere in the wave function, and that is, coding wise, a little tricky. All right, so this is where things are going pretty much from the single momentum, which I showed you today, the single momentum matrix elements, where we have already lots of cancellations, but as I said, some operators are not completely canceling, and so therefore we need to check this conjecture that they will actually eventually cancel if there's sandwich between the physical states. So that's the next step that I'm gonna take. So use this the setup there to show that these operators, matrix elements, actually indeed do cancel between the physical states, and then ask the first question: is this, what kind of symmetry or what kind of feature did really go into this? Is this specific to adjoint QCD? Is this specific to QCD anyways? Is this specific to 2 dimensions or something? These are questions that can be asked, or partially even have already been asked, and partially have been answered by others here in the audience. So that's kind of the outlook there. So conclusions are that we see that indeed it's a good idea sometimes to not just focus on the operators themselves, but actually on matrix elements. And these matrix elements are already zero, so there's no miracle, so to speak. If you're asking yourself, why do these results, these eigen functions and vectors, why are they so insensitive to the number of colors? It is because the Hamiltonian itself, if you write it down, the Hamiltonian matrix elements already are mostly zero, and that cancellation is pretty natural because of the structure of the theory, which has divergencies which have to cancel at all levels at finite n, as well, of course, as we already know at large n. So it's pretty much a very simple observation, and kind of a moment where you might say, okay, we could have anticipated this first already if we would have thought about this or checked this. All right, I guess that's all I had to say. A little short, but oh well.
Thank you so much for a nice talk. Get back.
Maybe I can make a remark. So we consider group equation, the gamma equal to the equation to the Lagrangian. If you look to the equation for single trace, the Lagrangian the equation close on themselves. All this real trace operators are connected to each other. But this holds, if the condition holds, it assumes Lagrangian factorization. I think the essence of your argument boils down to the Lagrangian factorization. And we have to ask ourselves, when does this factorization work? And for that, if I'm not mistaken, the necessary condition is unbroken one-fold symmetry. That's the thing that sort of makes QCD adjoint special, because in the case of QCD adjoint, you can take an arbitrary group and decorate it with adjoint value.
Right.
And for no other representation, you can do that. You can also do this, no other like symmetric anti-search for fundamental. But also for QCD, SQM cross SQM QCD, some Kuiper gauge theory with by fundamental fermions, it also has a ZM1 problem. But one can play the same trick. I think in both cases, all the corrections, as long as ZM1 forms to be downloaded, are destined to be one over n.
Okay. All right. Oh, yeah, question.
Possibilities for this to be all up. I thought one of the butterflies here was the one proximity is spontaneously both to fine. So I don't understand how to equal remind.
Okay. I was talking on the ordinance of QCD2 in my mind, in that case it's unbroken.
Yeah, yeah. So
Can I tell you something, however? Even, no, I will make this remark. Even in QCD2, when you compactify zero form parts, when you compactify 1% to transmute part of it, transmute to zero form,
Yeah,
and the part number of them. Basically, the necessary condition.
Yeah.
And if you do two form chorus, on both cycles, the zero forms are unbroken. And I think that they be sufficient to for the calculation. I'm not sure.
Yeah, okay, that would be certainly something good to check here, because as I said, it's a pretty unsophisticated, naive way of putting the theory, on the kind of on with, LIGO and gauge and so on. So it's a question, do we actually fulfill all these more sophisticated conditions? Here, all I'm reporting is basically I see these cancellations happening, and then can maybe talk why they're actually.
We'll go with this observation from eigenvalues of is the relative different factors, see over that as for. Is there a major common calculation to that all part of that work?
I've basically looked at just the matrix elements themselves. I've not done like looking at the mass difference or something, but I'm sure that you can reproduce that, yes. Yeah. But yeah, as I said, I've not looked at the eigenvalues themselves, but just at the matrix elements, and so that's before you diagonalize and get the eigenvalues out.
All right, if there are no more questions, let's thank you again.